Recording in progress.
Sure. Let's start off with this viscosity. So we have two plates. The upper plate is going with V and the bottom plate is going with 2V. And in the middle, there is another plate of area A. Which is going with V by 2. Viscous force is eta and 3D. These are few data points. Remember, if they give you eta is 60 poise, a poise is not an SI unit. You should write 10 poise is one SI unit. So be careful with that. And viscosity of liquids will increase, decrease with increase in temperature. For gases, it increases with temperature. So these are some theoretical things you should know. Let's get this. Find the force required to maintain the speed of the plate which you're pulling in the middle. And others do keep your cams on. Do you guys remember that formula, Newton's law of viscosity? F is equal to eta dA, eta A dV by dz. For thin layers, you can assume dV by dz is linear. If nothing is mentioned, take it as linear. Generally means it will be always linear only. Others cams on. Mm, mm. So if you draw FBD of the plate, you have your force F. Now be careful. The viscous force, right? It is not opposite to your velocity. It is opposite to the relative velocity. So here, this is going with V, this is going with V by 2. So what will the friction do? Friction will support the guy who is going slower. So actually this friction will be forward. Here, this is going with V by 2 and this is going with 2V. Both are going opposite. So this friction will be backward. Directions are important. Clear? You should not take it always opposite to the velocity. It is always opposite to the relative velocity. And what is the F1 ka value? F1 will be eta A relative velocity V minus V by 2 by distance between them, which is D. F2 will be eta A V by 2 minus of minus 2V by 3D. Therefore, F is equal to F2 minus F1. Are you clear with this? Most common mistake. People take F1, F2, both of them backward. That would be a mistake. Clear? Because the upper plate is going faster, the friction will try to oppose this plate and will try to support this. Clear? Not a difficult one, but you should know your formula and you should know the meaning of that. It is a V, there's a relative velocity. What about this guy? We have a long incline and you have a thin layer of fluid. On top of it, you kept a plank. It starts sliding. Find terminal velocity, plot VT graph, AT graph, and XT graph. I can actually ask you find the velocity as function of time t. Let's do that. Terminal velocity is easy. A plank of mass m is sliding on a thin layer of fluid on a long incline. The incline will never end. Initially starting from rest. Find the velocity of the plank as function of time t. What are the forces? If you take the plank, the forces will be mg sine theta. The viscous force will be backward. Acceleration, and let the velocity be v. Mg sine theta minus this will be eta a v by z. Z is the thickness. I should have given that. Is equal to mass into acceleration, which can be written as m into dv by dt. Then we have dv by g sine theta minus eta a by mz into v is equal to dt. Integrate 0 to v, 0 to t. This will be mz by eta a ln g sine theta minus eta a v by mz, and when you put 0, you'll get g sine theta. You end up with v is equal to mg sine theta z by eta a 1 minus e power minus eta a time by mz. There. It's an exponential decay function, and this term here would be the terminal velocity. If you just want to find v terminal, you need not do this much. At terminal velocity, acceleration will be 0. So you can directly say mg sine theta is equal to friction, which is equal to eta a v terminal by z. So you'll get the answer in one step. Clear with that. And if you just want to find the terminal velocity, that's easy. How will the graphs be? The graphs are important. The VT graph, it will start from 0, it will increase, become constant. This is VT graph. AT graph will look like this. Initially, you'll start from g sine theta, and the acceleration will tend to 0 at infinity. This is an AT graph. How does XT graph look like? That's an interesting one. XT graph, let me show it in one more page. At some point, eventually, the velocity becomes constant. In an XT graph, velocity, right, is a straight line. Tan theta will be V terminal. So your XT graph will be a curve. It gets closer and closer to this line, but it will never touch. You're getting it at infinity, velocity becomes constant. That means the curve becomes a straight line at infinity. Clear with that? So acceleration will keep on decreasing, tending to 0, but it will never be 0. Velocity will always keep increasing, tending to V terminal at infinity. And that X will try to, it will be a curve initially, and eventually it will try to become a line. The graphs are important. They can play with these graphs. And the tan theta will be V terminal. Clear with this? Mostly, if it is a mains level question, they'll ask you the graphs and the V terminal. They won't ask you the time thing, but yeah, who knows. Let's get this thing. We have two balls. Liquid ka density 2 rho, sphere ka density 5 rho, radius 2 r and 3 rho. Hope you guys remember the formula for V terminal. V terminal will be, in case you don't know, you know how to derive also. 2r square g by 9 eta rho b minus rho l. You should mug up this result. Let's get this. Find the ratio of viscous force after long time. Find V terminal. Find heat per second after long time. So we have two balls of different radius and different density. And this formula, Stokes' law, is only valid for spherical bodies. 6 pi eta. Let's see. So first of all, what is the V terminal there? So V terminal is 2 by 9 eta R square G rho B minus rho L. So this is proportional to R square into rho body minus rho liquid. So you have to be careful. If the densities are not same, it's not proportional to R square. It depends on the density also. So V1 by V2 will be R square. And what are the densities? 3 rho and 2 rho. By 4R square, 5 rho minus 2 rho. That would be 1 by 4 and that would be 1 by 3, so 1 by 12. And what is viscous force? F viscous is minus 6 pi R eta V. So this is proportional to R into V. So F1 by F2 will be R by 2R, V1 by V2, 1 by 24. What is the heat produced per second? Heat produced per second is nothing but force into velocity. So heat H1 by H2 will be F1 by F2 and V1 by V2. 1 by 24 and 1 by 12. 1 by 288. Clear with this? Yeah. Now in this, if you remember, there is one important discussion we had. As the ball is falling down, mg, you're losing gravitational potential energy. The viscous force is creating heat. And what is the buoyancy force doing? Do you guys remember that discussion? When the ball is falling down, your mg is losing energy. Great. So this energy has to go somewhere. One part becomes heat. Viscous force is creating it into heat. So if you look at the forces here, there is a viscous force and buoyancy force. Both together are balancing mg. So viscous force is creating heat. Buoyancy force is doing something. Everything doesn't become heat. So it is used to do what? Yeah, it is actually pushing the water up continuously. As it is sinking, water keeps rising up. So the potential energy of the liquid increases. You should check out the discussion in fluids. That was an important discussion. Here. As this body is going down, the liquid from the bottom will keep rising up, keep rising up, keep rising up. So even though if you look at the liquid, right, it feels the liquid height is not changing, but internally the centromass of the liquid is rising continuously. Clear? So you should definitely check out this thing. So buoyancy force actually does the work on the liquid to increase the potential energy of the liquid. So the ball is losing potential energy. In that, some is becoming heat and remaining is becoming the potential energy of the liquid. That's an important thing, at least in an advanced perspective. And it's a good theoretical question. So do check it out. Let's get this. What if you have two solid spheres connected by a string? Find B terminal. I can even ask you find tension in the string. We will discuss about that also, that potential energy thing. Let's see. What are the forces acting on this? There'll be two weights, mg, which will be 2 rho, 4 by 3 pi 2r whole cube g. There'll be one viscous force. Let's call it F1, which is 6 pi 2r eta v. This will be the bind force, FB, let's call it F2, which will be rho liquid, which is rho 4 by 3 pi 2r whole cube g. Tension will be internal, but if you want, you can find that also. This also will have its own weight, which is rho into 4 by 3 pi r cube g. This viscous force will be 6 pi r eta v. And this bind force will be rho liquid into, this is 2 rho. Then simplify this, we'll get V terminal from here. The two weights must be equal to two frictions, two viscous forces plus two bind forces. Hmm. There, it is just a matter of solving now. Let's get these two. We have two pipes. This radius is 2a, this radius is a, length is L and L. Left side the pressure is 2p naught, right side the pressure is p naught. Find the pressure at the interface. Do you guys remember the equation? Poiseuille's equation. dV by dt, the rate of change of volume flow, is equal to pi delta p r power 4 by 8 eta L. So you can treat the pipe like a resistance, where the resistance is given by 8 eta L by pi r power 4. They just work like resistances, series and parallel. In case you forgot, you should check it out. Poiseuille's equation. So in viscosity, primarily there are only three things. One is the Newton's law of viscosity, Poiseuille's equation, and Stokes' law. And the second one, same thing. It's a Y-shaped pipe. This is an important question. Like I said, this can be asked in fluid mechanics, capacitor, current, heat transfer. Mm-hmm. 33 by 17. I think 33 by 17. Yeah, most of you got it. So how do we do this? Like I said, the resistance R is given by 8 eta L by pi R power 4. So we can treat them as two resistors. Convert them into resistors becomes easy. So this resistance is R1. How much will that be? 8 eta L. L is same, R power 4. So if I take this is R, then this guy will be 16R. Agreed? All we want is a ratio anyway. This will be 2p naught, this will be p naught, and let this be px. Since both are in series, current will be same. What is a current? Current will be the potential difference, which is 2p naught, initial minus final, by resistance. Must be equal to px, which is initial minus final, p naught by 16R. R goes off, so that's what I said. We don't need that thing exactly. So this will be 32 p naught, 16 px minus p naught. 33 p naught by 710. If they ask you find the volume flow, then you can substitute px there, you'll get current. Current is the volume flow. Clear with this? The same thing we will do in thermal resistance. There, our thermal will be how much? Length by Ka. Remember that heat transfer? So same story. There the resistance will be R and 4R, and then you will solve. What about this guy? It is the same story again. So convert them into resistors. So it's like 3 resistors. This is an important model because it can be asked in 4 chapters. So 8 eta L by pi a. So let's call this guy R. 8 eta L by this thing. So this will be R by 16. That is 2R. This is 3p naught. Let this be px, 2p naught, and p naught. So you can assume current I is flowing from here, and you can assume this is I1 and this is I2. It doesn't matter. Choose any directions you want. So I is equal to I1 plus I2. What is I? You're flowing from 3p naught to px. By resistance R, I1 is going from px to p naught. In case it is reverse, the signs will take care of it. You don't worry. 2R plus px minus p naught by R by 16. Substitute, you'll get the answers. So they can even ask you this: find the volume flowing in this particular branch. So you can get it from here. Clear with this? Or sometimes the signs gets confusing. Like if you don't understand which one to take, then the best thing what? Assume all 3 are coming inside. I1 plus I2 plus I3 is 0. That is the best. No confusion. Like what is what. And we know that total current entering a node must be 0. That will take care of it. And others, if you don't keep your cams on, I'm going to start removing you. So let's get this there. This is the thing which I was saying. When the ball has acquired terminal velocity and it is sinking, what happens to the potential energy of the ball? What happens to potential energy of the liquid? What happens to the total energy of the system? Increase, decrease, remain same. This was the discussion I was saying. So when this ball is sinking, potential energy of the ball is definitely decreasing. There's no doubt about it. The total energy of the system is also decreasing because you're producing heat. The potential energy of the liquid is an interesting one. So if you just look at the FBD of the liquid, this is how it feels like. It feels like there's a cavity, isn't it? The ball, if you remove the ball and if you only look at the liquid, that is a cavity. This is the cavity of the ball. Because you're just looking at the liquid. Now, as the ball starts sinking, just look at the liquid. Liquid height will not change, but the cavity is going down. We can clearly see, even though the height of the liquid is not changing, initially the center of mass will be somewhere here. Center of mass will be somewhere here. Now center of mass will be somewhere here. The liquid center of mass is going up. So potential in the liquid increases. Is this clear? So that's what buoyancy force does. So buoyancy force is actually also conservative force. It doesn't dissipate energy. It gives you back. Clear with this? Now in this, if you remember, there is one more question. We have a plate which is rotating with omega naught. Then it is placed on a ground where there's a thin layer of fluid. This we did in the class notes. It's a good one. We have a thin layer of fluid which is thickness z and eta. Find the time when the disk stops rotating, or find omega of the disk as function of time t. You took a rotating disk, you spinned it, and you kept it on a fluid of a thin layer of a fluid. So it starts skidding on the liquid. And due to the viscous force, it slows down. You guys remember the spinning disk wala questions? It comes in total 3 chapters. Remember which chapters? Viscosity is 1. Friction में नहीं है. It's not in friction. Rotation में आएगा. A rotating disk is placed on a rough ground. Find the time when it stops. And the third time, it comes in EMI, electromagnetic induction. There is a disk there, and suddenly magnetic field B is switched on. Find the omega when B is switched on. Yeah. So this disk-based rotation things will come in 3 times. Anyway, we'll see when those chapters come. But let's do for viscosity. How do you take the elements? At a distance x, take a thin strip. Of distance x and thickness dx. This thin strip is rotating with velocity x omega. So on this thin strip, you have a friction acting backward. This friction will be eta, area of this thin strip, which is 2 pi x dx. dv, now what is dv? dv is the velocity between the thin strip and the ground. So you are comparing the ground and the thin strip. So that would be x omega minus 0 by distance between the thin strip and the ground, which is z. Are you clear with this? This will be tangential. The torque on the thin ring will be the radius into friction. That will be 2 pi eta omega x cube dx by z. So this is the torque acting on each ring. And since all the rings are connected to the disk, it's a big disk, you have to get the whole disk. So torque on the disk will be integrate this. 2 pi eta omega by z x cube dx. So this is the torque as function of omega. Pi eta omega r power 4 by 2z. But we know torque is equal to I alpha. I is nothing but mr square by 2. 2 goes off, 1 r square goes off. We end up with alpha is equal to pi theta r square by mz into omega. But alpha is nothing but minus d omega by dt because it's decelerating. Integrate this. You get omega is equal to omega naught e power minus pi eta r square t by mz. It takes infinite time to stop. Yeah, right behind. Clear with this. So first you have to integrate with respect to x, that will get the torque. Then again you have to integrate with respect to time. So there are two integrations involved. So this disk will never stop. A simple question would be like this. If there's a disk of radius r and 2r, how much effort you need to put when you find the torque required to maintain the speed? 16 times. The torque is r power 4. They can frame such kind of questions. Clear with this? Let's get this thing. Soap bubbles. We have two soap bubbles, one inside another. Outside pressure is P naught, surface tension is S. Find the pressure at point A inside. We have a V-shaped frame. Angle theta, length L and L. There's a soap film, surface tension S. Find the mass of the block M in equilibrium and find the time period for small oscillations. So this rod is, there is a soap film is connected to the rod and the block is hanging onto the rod. Hope you remember the excess pressure का formula in a soap bubble. P inside minus P outside is 4S by R. Remember like that. First was easy. Outside pressure is P naught. So here the pressure will be P naught 4S by radius, which is 2R. Let's call this PB. So pressure at A will be pressure at B plus 4S by R. So you just keep adding the pressure. And PB is 4S by 2R. So this is P naught by 6S by R. Easy. What about the next one? So in that V-shaped frame, if you keep a block M, what is the mass M in equilibrium? And if you pull the block and leave it, find the time period for oscillations. That would be a better question. Try. I'll give you a minute or two for this. So surface tension and SHM. M by 4SL. डायमेंशन मैच नहीं हो रहा है अंश Hmm. डायमेंशंस मैच नहीं हो रहे अंश. Mass M is easy. You just need to find the length of this black line. Drop a perpendicular. Theta by 2. This is length L. So this is L sine theta by 2. L sine theta by 2. Then we get mg is equal to, remember there'll be two surfaces, one on the front and one in the back. So film. So 2 times surface tension into that length, which is 2L sine theta by 2. Don't forget that so films will always have two surfaces. So that is your mass. You got it. Next thing, now when I pull this down, then what happens? Now when I pull this down, initially this was the position. Now when I pulled it, it came somewhere here. Like I said, we are not interested in the total forces, we are interested in the change in forces. So this distance was x, this was theta by 2. So this extra length you created is x tan theta by 2. Because you pulled the rod by x down, the length of the soap film in contact increased by x tan theta by 2. So therefore, the restoring force will be again 2 times surface tension into 2x tan theta by 2 is equal to minus ma. So A is equal to minus 4s tan theta by 2 by m into x. That's your omega square. You can take m ka value and substitute there. You can simplify it further. That's your time there. Clear with this? So initial length of the rod was balancing mg. So when you pull it down, you have increased the length which is in contact. So that extra length is this. So this is the additional length which comes in contact. Clear with this? This is another important question. So we have a loop of thread and there is a soap film surrounding it. Find the tension in the thread. So this question, right, can be asked in different chapters. So we have a loop of thread which is placed in a soap film. The soap film is stretching it. Hope you remember that. Find the tension in the thread. We have a ring which is rotating with omega. You generated a small pulse. Find the change in radius, or that is elasticity, or find the wave velocity. You can put a charge q and you can put a charged ring, lambda and r. Find the tension. You can put a current wire and a current loop. Find the tension. So you can ask this in 5 different chapters. You guys remember how to do this? Let's do this one. You have a thread which is placed on a soap film. Hope you remember the question. Right? When you pop the soap bubble inside, it becomes a circle. Find the tension in the thread. If you take a ring and if you rotate with omega, it generates a tension. Find the tension in the ring. On that, then find the change in radius of that ring. And if you generate a small pulse, there'll be a wave which is going on that ring. Find the wave speed of the ring. So, like literally, you can play around 6 chapters. I think after this, something which comes so frequently is your projected length and projected area. I think take a minute, then I'll show you in case you forgot how to do that. Let's see. So listen to the general process. So if you have the ring, you take a very small piece here, d theta. I'll exaggerate this. So we have tension here, we have tension here, and there'll be some force here. This angle will be d theta by 2, d theta by 2. First time you saw this was in circular motion. This is the tension here. This also will be d theta by 2. This also will be d theta by 2. So the vertical components will be t sine d theta by 2 and t sine d theta by 2. Till here, na, for all the chapters, it is the same story till here. So 2 times sine d theta by 2 will be equal to that f. For small angles, sine d theta becomes theta. So t into d theta becomes f. Now what is this f? This f, in case if it is a circular motion, then it will be dm omega square r, right? Where dm is nothing but m by 2 pi r omega square r. This is in circular motion. So if a ring is rotating with omega, find the tension in the ring, right? This f will be 2 into s into r d theta. This is in surface tension. So that arc length will be r d theta and two surfaces. The d theta will cancel. This will be m by r d theta omega square r. So the d theta will always cancel. If this was electrostatics, then this will be, meaning you kept a charge q in the center, and this was lambda. So the force will be k q by r square. The other charge will be lambda into r d theta. That would be your electrostatics. Suppose if this was the magnetic field and the current I is going here, then the force will be ILB. L ka place mein we get R d theta into B. This is the magnetic force. Clear with this? So by substituting the respective F ka value, you'll get the tension in 4 chapters. Once you got the tension, if you want wave speed, V wave will be root over T by mu. Mu is nothing but mass per unit length, lambda. But be careful. This is what? This is with respect to ring. This is not in the ground frame. That means you'll get two possibilities now. So when you generate a wave here and here, this guy will have a speed of v plus r omega. This guy will have a speed of v minus r omega, where v is that wave speed in the ground frame. Clear? And the other one they can ask you is elasticity. Young's modulus is equal to tension length by A delta L. So here the length will become 2 pi r. Area of cross section is A and delta L will be 2 pi delta r. So from here you can find the change in radius of the ring. Clear with this? Circular motion, surface tension, electrostatics, magnetic force, waves, and elasticity. 6 places this will pop up. Is that clear, everyone? This is what I keep saying. Just don't do it for one thing. Do it for as many things as possible. It will be easy to revise. Next thing. You have done this thing. We have a solid sphere. It is broken into n identical drops. Find the change in surface energy. Similar question in electrostatics. We have n mercury spheres of potential V. They're all combined. Find the potential of the big sphere. So these are two questions where you combine drops. One you break and one you combine. These are the two chapters that I remember. Is there anywhere else where we do something like this? You break drops or combine drops? I don't remember. If you remember, let me know. Let's get this too. Try. Everyone should try. Let's see. So when you break them into n identical drops, what remains same? Volume. So 4 by 3 pi r cube will be n into 4 by 3 pi small r cube. So what is change in surface energy? Surface tension, remember there'll be only one surface. These are liquid drops. S into change in surface area. That will be S into n times 4 pi small r square minus 4 pi capital R square. Take that small r and substitute here. R by n power 1 by 3. That will be S into 4 pi r square n power 1 by 3 minus 1. Clear with this. What about this guy? This is a good one. If you have n drops, then let the charge be q, 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 q. Then this charge will be nq. And potential of these things will be kq by small r. So the potential of the big sphere will be k. The charge has become nq. This is where most people forget. And the radius has become capital R, right? And that is n, k, q, and capital R is nothing but n power 1 by 3 into small r. So that is n power 2 by 3 into kq by small r, which is v. So if you combine n drops of mercury drops of potential v, you have to conserve charge also, you have to conserve volume also. The charge on the big sphere won't be q anymore, it will be nq. And the radius becomes the same thing here. So r is equal to n power 1 by 3 into small r. Clear with this? Can you find the heat released in this? Ignore surface tension. Find the heat released in that mercury drop. If I ask you that, how will you do? Let me do something else, then you'll get the hang of it. So see, we have a soap bubble, right? Let's do something more for this. Let's add a charge also. So we have a soap bubble which is charged. Charge is plus Q. Initially radius was R. Then you kept a pipe inside and you started blowing air, and this guy became 2R ka radius. Find the work done by the external force. Outside pressure was P naught. Surface tension is S. So we got a soap bubble of radius R, outside pressure is P naught, and it also has a charge plus Q on top of it. Now you kept a small pipe inside and you started blowing air, and the radius became double. The previous one you can actually do with capacitors, remember? Each cell is a capacitor of C. So you can find Q square by 2C n times. The final thing will be NQ ka square by 2 times C new capacitance. So find the change in energy. That will be the heat produced. Or you can use self energy also. That also works. Let's get this. Now you got a clue for this. There I combined three things: work done, surface tension, and electrostatics. Again, they might not exactly ask this kind of question, but the point is this: trying to put as many things into one question, we are revising 3 to 4 concepts in one go. That's how you should revise. And this will actually form the basis of foundation for advance also. As advance may they'll ask you, and drops are mixed fine heat produced. Let's see. So few things happened here. When you started blowing this, first of all, the area increased. So work done by external force will be change in surface energy. So that will be S into, again, soap bubble. So 2 times S into surface area, which is 4 pi 2r whole square minus 4 pi r square. This is a change in surface energy. Plus, you also pushed the atmosphere. So P naught into delta V. This is work done on atmosphere. You're pushing the atmosphere outside. Basically, you're compressing the atmosphere, where delta V is the change in volume, which is 4 by 3 pi 2r cube minus 4 by 3 pi r cube. So that is there. Plus the self energy. If you remember the self energy ka formula, k q square by 2 times 2r minus k q square by 2r. Remember hollow shell ka self energy? This is change in self energy. And we are assuming the temperature is constant. If temperature changes, then you'll get delta U also, change in internal energy. Formula याद है उसका? NCV delta T. You can play like that also. Then you can say temperature became T to 2T. Then you'll add up one more term, internal energy ka term. You can keep playing. Play with this. I hope you remember the result for this. Two soap bubbles coalesce. That is a word they will use. Coalesce meaning they got stuck basically. Find the radius of the intersection and find alpha, beta, gamma. This is a pretty standard question, right? Should definitely know. This will pop up in some or the other exam. Direct formula, there's nothing there to solve. You should know, that's it. You won't have time to derive in the exam. Yeah, so the formula is 1 by r is 1 by r1 minus 1 by r2. Suppose if r1 is equal to r2, r will be infinity, meaning it becomes a line. The shape would have looked like this. And alpha, beta, gamma will be 120 degrees. You can check out the notes for the explanation. It doesn't matter whatever is the radius, the angles will be always 120. Clear with this? Take a break. Come back in 5 minutes. We'll continue from here. Chalo, let's get these things. So we got a capillary here, V of length L, and it is placed inside a liquid. The height of the liquid is h. Now you remove the capillary and you again pour the liquid inside. And we observe the liquid inside, right, will get stuck inside for some level. Find H dash. Got the question? When you kept the capillary inside the liquid went to a height h. Now you took out the capillary and you started pouring liquid inside. And you observe some liquid gets stuck inside the capillary. What is the length of the liquid that gets stuck inside the capillary? Hmm. If a capillary is placed in an orbiting satellite, surface tension is given, theta is given, density of water is given. Find h. What happens? So, if you look at this capillary here, the reason the water level is rising is because of this one meniscus. We have one meniscus here, which is pulling with a force of 2 pi rs cos theta. That is balancing your mg. Agreed? If you remember the derivation. Now, when you remove it completely, I'll just draw a bigger one. When you remove it completely, and when you pour liquid, you actually get two meniscuses. You'll get one more drop here, na? So there'll be one surface tension here, and there'll be one surface tension here. The liquid at the bottom will also form like a drop. Getting it? So there'll be two surface tension forces. So now you can balance 2 mg. So the height will be 2h. Under the assumption the length of the tube is sufficient. So if L was greater than 2h, then the answer is h dash is 2h. If length was less than 2h, then the answer is h dash is equal to L. Making sense? Suppose, let's say, you can balance water up to 60 centimeters. But what if length of the pipe is only 40 centimeters? Means the water will be fully filled and it won't come out, isn't it? It also depends on the length of the pipe. Are you clear with that? Why it depends on the length? Technically, it can balance 2h ka height. But there should be enough pipe to balance 2h, isn't it? What about this thing? Height of the capillary? This will be fully filled. Yeah, last time we did this thing, so you remember. So be careful. Just because they give the data doesn't mean you have to use it. What about this thing? What happens if you keep a tube of insufficient length? The formula is still valid. H is equal to 2s cos theta by rho gr. H will change and theta will change. So when you keep a tube of insufficient length, H decreases, isn't it? Because you're not going to the maximum value possible. H decreases, so cos theta decreases. That means theta increases. Meaning, if you actually try to see what happens with tube of insufficient length, let's say liquid can actually go till here. This is how the meniscus will look like. But if you keep a tube of insufficient length, let's say if you only keep it this much, right, the surface would become something of this sort. The surface curvature will not be same. They'll have different radius of curvature. This will be r dash and this will be r. R dash will be greater than r. Think about this. When the height of the tube is almost zero, liquid surface will be flat, meaning r will be infinity, right? So the radius of curvature will keep changing. And there's a simple reason, like when you take a full capillary, you can clearly see there is a symmetry. When you take insufficient tube, the edges are messed up. So the contact angle won't remain same. And you guys remember this heat produced in this? Last time I was saying something. In a capillary, what is the heat produced? Let's say if we take this height to be h. The force will be 2 pi rs cos theta. This will be the center of mass. 2 pi rs cos theta is equal to mg. The heat produced will be 2 pi rs cos theta, that is a force, into displacement minus mg h by 2. This will be mgh minus mgh by 2. Half of it becomes heat. Clear? So the surface tension force will pull it up to a height h, but only the energy is stored up to the center of mass thing, so h by 2. And if you observe, this is always the trend, isn't it? When you take a capacitor without a resistor and put a battery, the work done by battery is QV, whereas energy stored is half QV. You always get. Why there is 2 mg? Yashil, not clear? There are two meniscuses, Nare God, so there will be two pi rs cos thetas. If one 2 pi rs cos theta can balance 1 mg, then 2 will balance 2 mg. No? Clear with the heat produced thing? This is a general formula for any random surface, if you remember. The excess pressure, right? P concave minus P convex is S by 1 by R1 plus 1 by R2. So what if you have a cylindrical meniscus? What will be the pressure inside? So this is a straightforward formula substitution. So who is concave and who is convex? So this guy is concave. So concave is outside here. And for a cylindrical surface, what is the radius of curvature, everyone? For a cylindrical surface, one radius of curvature is r, the other radius of curvature is infinity. Straight line. So the formula becomes S by 1 by r plus 1 by infinity. Here concave will be P naught and this will be P inside. So pressure actually will be less. That is the reason. Did you ever notice this? When you have, plates which are placed in a water, when you take out the plates, sometimes the plates stick together. Kabhi dekha? Meaning it used to happen a lot in our hostels and IIT mein. So they used to have a big tub and they used to just put the plates inside. So when you try to take out the plates, two plates used to come out. So between the plate and the plate, the thin film of water used to get stuck. And because the pressure is less, the atmosphere is pushing from both the sides. They used to get compressed. So you need to put a small gap and let the air enter inside and then it comes off. Clear with this? This is another good one. The heat producer we just did. So we got a thin capillary of massless, which is placed inside the liquid. Now you're trying to pull it out, or you're trying to keep it at rest. Find the force required to keep the capillary at rest. Second one, you have a container with a hole at the bottom. It's a small hole of radius. At what depth will the liquid enter inside? So if you have a container with a small hole and if you push it into the liquid, immediately the water won't enter inside. Hmm. Right, Vihan. MG नहीं है रे आदित्य, massless ना. Let's see. What is the catch here? Now, the most common mistake, right? You need to understand. If I draw the capillary here, there are two things happening here. Understand the water outside is also sticking to the thing, and there is also a meniscus inside. So if I actually draw the FBD of the capillary, the liquid which is inside is being pulled up, vice versa, that will pull it down now. Newton's third law. This force will be 2 pi r s cos theta. Similarly, there is a surface which is also outside, which is also pulling it down this way. That is also 2 pi r s cos theta. So in order to balance this, are you getting it? There are two meniscuses. There is one outside, one inside. The one outside we always used to ignore because it didn't matter, because the height of the liquid inside will depend only on the inside force. The outside capillary didn't matter. The outside this liquid rising up didn't matter. But for the pipe, it would matter. So this will be 2 times 2 pi rs cos theta. If the pipe had weight, also add mg. Are you clear with this? You need to apply double the force of that meniscus or else this will sink inside. And what about this thing? As the water is entering inside, eventually it will form a bubble. So if I try to draw it in a big one, it forms a bubble like this. So here the pressure is P naught. Here the pressure will be P naught plus 2s by r. When this pressure, let the depth be h. So when this guy becomes P naught plus rho g h, the bubble will pop. H is equal to 2s by rho g a. The formula comes out something similar to this thing capillary. So as you're pushing it down, if you remember, the bubble doesn't become like this. Initially, the bubble will look like this, little flattish. You push it more, it will become little better. If you push it more, at some point, it becomes a proper hemisphere. At that point, if you push more, it will pop. Clear? Check out the notes in case you're still confused. We did have a good discussion on that. Let's see this thing. So we have a rod here. You're pulling with force 100 and 100 on both the sides, 1 meter, 2 centimeters. Young's modulus is given. Sigma Poisson's ratio is given. Find the change in length and change in radius. In case you forgot what is Poisson's ratio, sigma is nothing but lateral strain delta r by r by delta L by L. And this is one important question. If volume is constant, then sigma is 0.5. That itself is a question. There are very few questions on Poisson's ratio. That is one of them. If the body volume of the body is constant, find sigma, Poisson's ratio. Let's get this. Did you see? First day of the class when we started, we had around 54 people. Today when we started the class, we had 37. Now we have 32. That's what I'm saying, in today's world, right? You need not be a super genius. You just need to turn up every day and your competition, half of the competition will get wiped out. Now people think, they didn't get into IIT or they didn't get into good college or a good job because, they are not smart enough. Nah, there's nothing to do with intelligence nowadays. All of you are pretty smart. People just can't do one thing consistently every day for a few months. And keep seeing this thing. By the time we reach advanced sessions, we'll have around maybe 2022. If more people stay, I'll be happy. But then again, let's see. And anyway, I think some of them had prelims anyway. So I think there are at least 7, 8 people who informed me they had prelims. I said, then it is fine. If it is your first prelims and you have not written before, you should definitely focus on prelims and score 85%. Don't ignore boards. It will come to bite you very badly in the end. People who have written here 3 hour ka boards paper, you would have realized. It gets really frustrating. Hand starts paining. Right? All different problems come in life. How to do this thing? So Poisson's ratio, remember that it's pretty straightforward. So delta L is easy. Y is equal to tension length by A delta L. Hope you guys remember the tension. What's the tension in the rod? 200. 0. Tension is 100 only. Be careful. So from here we'll get delta L by L. Substitute all the values. Then sigma will be minus delta R by delta L by L. Substitute the values, will get delta. There you got everything. Clear? Let's do this question. We have 2 walls here. This is a standard model. We kept a block M hanging in the middle. The length of the string is initially was L, Young's modulus was Y. This is X. If X is much smaller than L, find X. Remember this question? We had a rope of length L tied between 2 walls. You hanged a block in the middle and then it got depressed by X. The wire is massless. Find X. You can take other values you want. A is the area of cross section. Y is the Young's modulus. L is the total length. Y is tension 100. Whenever you want to find tension in the rod at any point, you have to cut it. So if you're pulling with F and if you're pulling with F, and when you cut it here, and if you draw the FBD, this tension, since it is at rest, T must be equal to F. Ask yourself, if T is double, that means this piece will start moving. Right? So more about this, you should definitely check out the NLM notes. We even had a Horska picture. I'm sure most of you remember this. There is a Horska picture. This was the discussion. You should check it out. Finding tension in a string or a rod. So you need to understand, tension is not some external force. Tension ka job is not to, give you double the force or anything. It's simple thing. It will try to restore the body. If you're trying to pull, it will try to oppose you. Right? So if you're pulling with F and F, simple mathematical explanation, acceleration is 0. If you cut it here, this is F, this must be tension, acceleration is 0, therefore T must be equal to F. If T is not equal to F, the piece will move. But we know it is an equilibrium. Clear, no? Yeah. Yeah, that's a thing. People do get confused, like, in a flow exam, people put it double, some people think 0. Happens. Because I shouted on you about that a lot of times, you guys remember. And why do you think I tell you that story about horse and everything? Even if you don't remember the damn result, you'll remember the story, so it will connect. क्या करना था? Let's solve this thing. This is a good one. I want the result. The simple question would be this: x is proportional to L power x, find L power n find n. ऐसा कुछ होगा. नहीं रे बोलो था. Right, Aditya. So कुछ आएगा. So let's take this as theta. Since x is small, theta also will be small. So what was the delta L? Delta L will be, this length was L by 2. Or you can actually do like this also. This will be 2 times root over L by 2 whole square plus x square minus L. That is a change in length if you don't want to use theta. Then take out that L by 2 common. Then this will become 1 plus 2x by L ka whole square whole power half. Since x is much smaller, I can use binomial approximation. This will be 1 plus half into 4x square by L square minus L. L will cancel. You end up with 2x square by L square. This is the change in length. And what is the tension here? If you take that as theta, this is the tension T cos theta. So 2T sine theta will be equal to mg. For small angles, I can write sine theta as tan theta. And the tan theta will be opposite side x by L by 2. So from here we get tension is equal to mg L by 4x. Then apply Young's modulus is equal to tension length by A into delta L. Substitute here. This will be y, tension will be mg L by 4x. Length is L, area is A, and this is 2x square by L square. I think एक extra L आ गया guys.
Actually, del L should be 2x square by L. Because I was calculating it.
Yeah. I'm just testing you guys to see whether anyone will find out. I did a mistake there. चलो then यहाँ से x cube आएगा, and that would be, I'm telling you now, वो extra L आ गया था, सही है. Then that was 4ay. There. So that x will be mg by 4a, 4 or 8, वो 8 है. 8ay whole power 1 by 3l. So yeah, you got it. Clear with this? It's a good one. So know this thing. Yeah, these are the formulas. Like I said, elasticity, right? It's pretty straightforward. If the tension is not constant, this is the formula. If energy is stored, this is the formula. Do you guys remember this? Half stress into strain into volume. Better than that, this I like, because you can write strain as stress by Young's modulus and you'll get this. And if F is there, this is the, elongation ke liye there's a shortcut. If you have F1 and F2 both in the opposite direction, then you can take F average, F1 plus F2 by 2. Both are in the same direction, you can take F average, F1 minus F2 by 2. Elongation will come. But this will not give you energy. Energy you have to integrate again. So remember this results, quite useful. So if tension is variable, use this. Tension is constant, regular formulas will work. And this is just a shortcut. If you have variable forces F1, F2, if they just want elongation, you can get it faster. Now let's get these three then. So we have a rod here, mass m length L, Young's modulus A sub hanging. Find the ratio of elongation in the upper half and the lower half. I can even ask you find the ratio of energy stored in the upper and the lower half. B part, there are two rods, Y1, L1, Y2, L2. Find Y equivalent. Third one, two rods in series. Find the time period for small oscillations. Out of all the chapters, the chapter which just goes into anything is SHM. It's like cherry on the cake. The whole question belongs to some other chapter. In the end, it will come and say find time period. It literally hijacks the whole problem. So if someone tells me now you have to revise with only one chapter, I'll take SHM. You can literally do everything, even thermodynamics. Let's finish off. We might wrap up a little early only today. We are done mostly. Elasticity, there's really not too much. Hmm. Let's see. So how do we do these kind of questions? At a distance x from bottom, we find the tension here. The tension will be only due to the weight of this. So tension will be m x by L into G. That's your tension. So the elongation ka formula is integral T dx by A y. Right. So E lower by E upper will be integral mg x by L dx by ay. So the lower limits will go from 0 to L by 2. by integral. So the integration is actually the same thing, only the limits get messed up. L A y, the limits will go from L by 2 to L. I think you'll get 1:3, I guess. Clear with this? Think about this. The upper part will have more tension than the lower part, isn't it? It should elongate more. And similarly, you can do for the energy also. What about the y equivalent? Now, this you have to be careful. Most people go for this. You want to replace this with a single rod, y equivalent, and length is L1 plus L2. So be careful with that. So when you keep them in series, what will be same? The tension will be same. So that would be how much? Just do it in one more page. So elongation in this rod is E1, elongation is E2, and let the elongation be E1 plus E2. So E net. So E is equal to E1 plus E2, and the elongation ka formula is what? Tension, length L1 plus L2. So tension is same in all of them. By A, Y equivalent. This will be TL1 by AY1, TL2 by AY2. T will cancel, and you will get L1 plus L2 by Y equivalent. Is L1 by Y1 plus L2 by Y2. That's how we get Y equivalent. Be careful with these equivalent wala questions. Huh? You can also ask this in thermal expansion. Find alpha equivalent, find Y equivalent. So these things are important. This thing is what? You can clearly see that tension is equal to YA by L delta L. This kind of looks like F is equal to Kx, isn't it? So each wire can be treated like a spring whose spring constant is YA by L. So you can replace this with the springs. This is K1 and this is K2. And springs in parallel, what will be K equivalent? Springs in parallel, K equivalent will be K1, K2 plus K1 plus K2. And the time period will be 2 pi root over M by K equivalent. Is that clear, everyone? Let's get this through. This is an important thing. If you apply with a constant force, you should definitely go and check it out. If you think of this like a spring and block, right, it will start oscillating. So work done by the force, we have a full discussion on this. You should definitely go and read that once. What happens if you pull with a constant force and this? ये question याद है ना? Standard result, I should remember this. Replace the area with pi AB. Don't forget that comes 3 times. There. So if you pull with a constant force, work done by external force is Fe, energy stored is half Fe, so heat produced is this. But if you pull slowly, that means the external force is always equal to the tension. In that case, there'll be no heat produced, there'll be no oscillations. So you should check it out. So F is equal to constant and the heat produced is half Fe. Here, this will be zero heat. This thing, remember? In which region material is plastic? Do you guys remember what is plastic? Even when you decrease the tension technically what should happen? If you decrease the tension, elongation should decrease. Means if you decrease the stress, strain should decrease. But in the region A to B, the stress is decreasing, but strain is still increasing. That is the meaning of plastic. Plastic meaning find the region where stress decreases, but strain increases. Logically, it doesn't make sense normally, but what happens is the metal structure got destroyed so much, right? It'll start elongating on its own. What about this thing? Which has more Y? I hope you remember. Here, na, let me discuss few things. In NCERT notes, we wrote something. NCERT may actually had a different statement, so we need to change that. So for this, if you take this angle theta, this O to A is a straight line. Slope of OA is tan theta is Young's modulus. There are some really good questions on this graph. So look at this. From O to E, remember what is E? E is the elastic limit. A is the proportional limit. So basically from O to A, forces are linear and conservative. O to E, forces are conservative, but A to E, they're not linear. U is the ultimate strength and B is the breaking point. So here, this was the change, which recently Aditya had a discussion with that. So this UB is actually proportional to ductility. It is not E to U, according to NCERT. So we will just follow them. But another, because actually once you cross U, it breaks off. I don't know why they gave it that way. Ductility. Remember what is ductility? Ability to make into thin wires. So it is not EU region, it is UB region. Right? Other sources say E to U, but yeah. So we'll stick with that. So in this graph, these are all the questions I can ask you. What is Young's modulus? Slope of OA. Right? Up to what region the forces are conservative? O to E. Up to what region Hooke's law is valid? O to A. Which region gives you ductility? U to B. Clear with this? Which region is plastic? U to B is plastic. Clear? These are all the questions on the graph, stress strain graph. Other than that, we have formulas again, bulk modulus minus dP by dV by V, adiabatic gamma P, isothermal. We will do this again in thermal expansion, but do you remember? If you put a rod on a smooth surface and if you increase the temperature, find the thermal stress. It will be 0. And this is one important result. If you keep two rods, Y1, A1, L1, alpha 1, Y2, A2, alpha 2. If you increase the temperature, find the distance moved by the interface. This is the result. We'll do one question on bulk modulus though. Shearing stress ka formula, and I hope you remember this twisting torque. And these results are important, right? 2023 there was a question on this. They gave a direct result in 2023. This is a relation between the Young's modulus, bulk modulus, rigidity modulus, and Poisson's ratio. Let's do one question. So let's say we have a liquid. We have a small ball here. Radius R. Bulk modulus B. The base area is A. Right, and someone took a block M and they dropped it into the liquid. So initially the radius was R. Someone took a block of mass M and they dropped it inside. And the block is floating. Find the change in radius. I'll draw one more picture, wait. something happens. If the change in rate is delta r is much less than r, find delta r. This is a good one. I mixed up two different things. What's the catch? When you drop the block inside, if you draw the FBD of the liquid, you will realize initially the liquid will have a weight of some, let's say, capital mg. Let the block come as be small m. Most people don't understand how did the pressure increase. What is the pressure on the base? The weight of the liquid mg by area. Now when you drop that, now what is the total force acting? This mg. Understand this thing. This is actually what is happening is this. If you draw the FBD of the block, the buoyancy force will act upward on the block. That same buoyant force will act downward on the liquid. Are you clear with this? So now the pressure on the base will be, and that is important, will be mg plus the buoyant force by area. So I can actually ask a question like this, what if I drop a block which sinks inside? Then FB will not be equal to buoyant force, isn't it? FB will not be equal to mg. So here this will be mg. So basically this is mg plus small mg by area. So the delta pressure is nothing but small mg by area. Clear? Once you got delta P, you're done basically. That will be how much? Bulk modulus is equal to minus delta P dV by V. dV by V is nothing but 3 times delta R by R is minus delta L by B. Delta R aa jayega. Minus indicates it got compressed. So by making the block float inside, you increase the pressure at the bottom. Because of that increase in pressure, the ball got compressed further. Clear? And the answer will change if the block floats and the block sinks. If the block floats, buoyancy force is equal to small mg. If the block sinks, then the buoyant force will be rho liquid volume of the body into g. Clear with this? That whole term will change. You can play like that with this. Okay, so that is there. Few questions on this. Go through the notes. There are a few more models, but I think this much should be fine. So next class, when we catch up on Friday, we'll be starting with ray optics and wave optics. So first we'll start with ray optics. Quite an important chapter. Again, there's a lot of formulas. In total, in bunch, I think you'll find more than 20 formulas plus. So definitely make sure to go through this, but quite an important chapter, has a pretty good weightage. So, okay, with that, we'll wrap up for that day. So those are out, so you can stay back, or else others are free to leave. I'll see you guys on Friday, same time. So take care, stay safe.